So we're here at the ARM TechCon 2011.
Yes.
So who are you?
My name is David DeHarnay, and I work at Cadence Design Systems. I run product management for silicon realization.
So what does Cadence do?
Cadence provides software that enables, or I guess fuels, semiconductor and electronics design. So anything that goes on a system on chip, or any silicon that goes into a package, goes onto a board, goes into something that you know and love, maybe an iPhone or something, right? Anything that goes inside here, we have one way, shape, or form we touch it.
So you were involved with what made it possible?
Well, all the silicon that's inside of here, all that silicon, all those chips sit on a board, and that board goes into, all that silicon sits in a package, and that package goes onto a board, PCB board, and that PCB board sits inside something like this. And no matter what, no matter where, any kind of electronics that's built in the world uses Cadence.
So is in the SoC or is outside, it's both?
It's both, yeah, it's both. It's both on the SoC itself, plus on the PCB. Plus, when you start looking at the value, if you look at something like this, the value is not just the device, although that's also very cool. It's what you can do on the device, and that's software. So when you start looking at hardware, which is this, or the chips is considered hardware, the real advantage starts to come from the software. It's the functionality that this allows you to do. So hardware and software combined, we touch all of it.
So there's a CPU die, it's called, right?
Yes, yes.
And there's a certain amount of power you can use,
Correct.
and you try to fit as much as possible in there?
Well, so the key is when you're starting to have embedded processors, you need to have the smallest area possible, because I'm using this as an example because it's in my hand, but the thing that you're using to film this even, it's small. Small is the key. So the form factor or the area associated with all those chips has to be as small as possible. That's number one. Number two, you have performance requirements. You need this thing to respond quickly. And so that's another trajectory, is the performance of the system itself. And then the power. The power profile has to be as minimal as possible, because this is no good to me if it only lasts for an hour, as an example, and neither is what you're using.
So do you just make, your product is basically software, and software engineers sit behind a computer and use your software?
That's correct.
Is it more than that?
So our software is like CAD, so computer-aided design. And people think of CAD as being things you'd use to design a bridge or a widget of some kind. Well, CAD, or computer-aided design, is also used to design chips. And so our company is a premier provider of CAD software for the electronics design industry. And so Cadence is that we offer a full array of product lines, or software products people sit down and they design with to create their electronics or their semiconductors.
So it's basically companies like Texas Instruments, Qualcomm, and all these, they're your customer, or
Absolutely.
it's even much more than that?
Well, it's much more than that. I mean, first of all, there's the customers that are designing semiconductors, so that's one thing. So you have a lot of these, what they're called fabless semiconductor companies. So you look at companies like NVIDIA, or you look at a Broadcom, or a Qualcomm, or you go over into Asia, you look at all the Indian companies that are out there, or in Asia, specifically in Korea, where you look at Samsung. Those type of customers. The other piece of it is system-level companies. So if you think of Apple as a system-level company, right, or if you think of Samsung as a system-level company, they do more than just the chips on there. They do the whole enclosure, right, the whole package, everything. And so we have customers on that area. We have customers on the silicon area. We have customers on the SoC area. But even more so, when we start looking at hardware and software, we're opening up a whole new realm of opportunities for our company.
So let's say, for example, there is a Cortex A9 tablet coming out.
Yes.
So how much of that software work is done by the chip maker?
Yep.
And how much is done by, let's say, a little tablet company that releases it?
Well, it depends on the...
Based on how much they use your software.
So actually, ask me the question again, I'm sorry.
So what I'm trying to ask, let's say there's this company, Arcos.
Yes.
They're doing this tablet here.
Yes.
And there's a TI doing the processor.
Yep.
So who's using Cadence the most?
Oh, in this case, in fact, both would be. Right, both would be. So in the case of a TI, they would be supplying chips that go onto that board. So anything that touches the silicon, the pack, this company's probably doing the board work as well as the enclosure. So when you start looking at, there's a couple of different factors. CAD, that computer-aided design, is a broad topic. There's electrical CAD, ECAD, which is the area that we play, and then there's mechanical CAD, or MCAD for short. So the package this goes into, this whole thing you're looking at, the pretty user interface, that's MCAD. It's mechanical CAD. Now, what's going inside of this is electrical CAD. It's ECAD. So the software that we provide is distinctly in the electrical CAD area. So with this company, they're probably using our stuff for all the package and the board elements. TI would be using it for the silicon elements, right? MCAD companies like Dassault, MCAD companies like PTC or parametric technology, or even on the lower end would be an AutoCAD, which you've probably heard of, right? Is that we have interfaces built between MCAD world and ECAD world to facilitate this company building a product like this.
So that it holds together and works.
Exactly. And it has to be validated and verified and everything, because anything along that chain, something goes wrong, the whole thing's broken, right? So you have to be able to have that validation and verification all the way through.
So how do you validate, virtually or for real?
No, we do it for real. Yeah, no, it's done basically looking at simulations, simulation models with the analog piece, simulations for the digital piece, mixed signal, because analog and digital is mixed signal simulation. That's just at the SoC level. But then you get into system level verification. So this is cool because it's got really interesting software that runs, right? Well, that software, I mean, you start looking at it, this device is cool because of the software. But if we do it right, this software, the hardware that's in here should be touched in the best optimal way, because that software should understand how that hardware works. So what we've concentrated on is making sure that software and hardware are co-developed, co-verified, and co-optimized. And that's what holds this thing together.
Sometimes there are basically kind of like reference designs that are out there, and where many different tablet companies use it similarly.
Yes.
And some other times the tablet maker might do more customization and use the software more.
Yep, that's true. That's absolutely true. I mean, if you start looking at trying to get to market quickly, right, you want to reuse as much as you possibly can, and if somebody else can take something that's preset, like a reference board, they'll do it, right? A reference board with a little bit of optimization, that's an ideal way to go. But, you know, for high-end companies, and I would say an Apple as an example of that, or Samsung as an example of tablet makers, right? They're going to do their own thing. They'll have a reference board, but they're going to do better than the reference board because they have their own special sauce that they bring to it. But by and large, it can be an expensive and risky proposition to do that unless you really know what you're doing. So when you see the plethora, or that just enormous amount of tablet makers and new tablets coming on the market, I'd say a lot of them are trying to pull off the shelf as much as possible. But the really good high-end ones they're doing it, you know, pretty much full custom.
So there are some rumored articles coming out that Apple has 1,000 chip engineers working at Apple, and that could be true. So there's Samsung doing a bunch of stuff and Apple doing a bunch of stuff.
Sounds like maybe even a low number.
Low number, yeah.
I think that may be a low number. But yeah, there's a lot of horsepower. A lot of horsepower goes into making these, yes.
So how do you have 1,000 people collaborate and using your software? Do you do collaboration software?
We do, actually. So what we enable, first of all, when you start collaborating across multiple geographies or even multiple product lines, really important that tools that are let me put it this way: if you've got a design flow for anything, you start at this end and ultimately you want to get to here, and there could be 100 steps in between or 1,000 steps in between. Sometimes these are tools that are in the flow, sometimes they're unique value add that engineers bring to the table that are in the flow. But the end goal is to get to here. Okay. So when you start looking at in terms of software and how it's relevant in that whole spectrum, what we do to make sure a collaboration happens is that every step along the way has to have a visibility to the end. So, or for example, when you start off, you know what your specification is for power. Say you want 30 milliwatts or 3 milliwatts or something. You know that up front. That's your spec that you want to go to market with. Or you know that you're going to have a device that's a certain size, and therefore you have to build it to that certain size. Well, if you know that up front, how do you pre-program that information in a way that every tool and every engineer along the way knows what to do without having to reinvent the wheel? So in terms of collaboration, there's one really rudimentary element, which frankly a lot of people miss, is that flow has to be very connected, first of all. Second of all, things like team design, literally... Sorry. No problem, man.
Oh, no, I'm sorry.
No, you're cool. So things like team design are really important because, and what I mean by that is you can look at, let's take this device again. So you take the PCB board that's happening on here, right? And you take, and if we could rip it apart, but I'm sure you wouldn't be happy about that. But inside here is a PCB, right? Or a multiple layer PCB. Well, the design teams that made this are all over the place, right? So if they're all over the place, how do they make sure that they stay connected? So we have in our software something literally called team design, which allows somebody to touch the PCB design or the design that's inside at the same time somebody else's, and we keep version control, allow people to work in a very collaborative fashion. And if you think about a very popular company that if we put this in the realm of say consumer use, right? Google, right? Google has a way to do collaborative work, right? Or something like a live meeting, or something that allows you to do real-time collaboration with peers. We have that built into our software in many respects. So teams around the world in real time can actually collaborate together on a single project. So we do it both from the design flow, making sure the tools run together, inputs and outputs all match, making sure that there's visibility and predictability all the way through, but also allowing for that real-time, I wouldn't say real-time collaboration environment.
Does Google use your software a lot?
Motorola, because Google is obviously they make their money in ads, right? But their recent acquisition of Motorola, the mobile, right? That's a really interesting development in the industry because it just shows the criticality of how software plays a dominant role in the hardware. So software Google being a software company starts to go look at if I can pick up a Motorola mobile. And their tablets and their phones and everything, there's no end to the amount of customization I can bring to that hardware if we plug and play nicely together. So with the acquisition of Motorola, now this becomes really relevant.
But they want Android to work as good as possible on all the chips. So so basically they use Cadence every time to optimize for every chip.
They would, right? But in the case of Android, so software is independent, right? You have to verify that software, that it works on the hardware. And then what they'll do is they'll have a prototype of this, right? They won't have the finished product, they'll have a prototype. And in that prototype, they're going to be validating that their Android operating system is doing what it needs to do on this system. And so where Cadence comes into play is we do the prototyping. We do the prototyping, we do it in software, we allow that collaboration of hardware and software verification and design. We allow that so that when Google is trying to optimize the device for their software, Cadence is an ideal solution for that.
All right, and the latest R&D that you're doing for the Cortex A15, what kind of R&D are you doing? What's the future?
There's a couple of things. Let me put this down for a second. So there's a couple of areas that become very interesting, which I think are very unique to what we're providing. So ARM is fantastic at what they do. Embedded processors, they're everywhere. Mobile is going through the roof. People are excited about the next big thing that comes out. When you look at design tools and how Cadence enables the best performance that you can get, and the best area and the best power profile on a chip, there's a couple unique technologies that we bring to the table. One of them is called CCOP, which is clock concurrent optimization. Now, for those of you that aren't aware of clock design, effectively this is a multiple stage process. What we've done and we've innovated is we brought now to market something called clock concurrent optimization, which really brings together the placement and the clock tree and the post-clock tree optimization steps into one. It shrinks down the time, very intelligent optimization, and here's where the benefit comes. So that's all techno speak, right? But where this becomes interesting is where the customer starts to realize the benefit, and the benefit is a 10% performance improvement over a traditional method. You get a 30% smaller area on your die, or you get a 15 or 20% performance improvement, power improvement. So that's where clock concurrent optimization is a very big deal. It's what we would say is sustainable differentiation because it's so unique what we're bringing to the table. That's one thing. Second thing is 20 nanometer. 20 nanometer is the next generation that people are starting to move to. So when you look at the opportunities for 20, it's all about performance, area, and power. And we've tuned our Cadence flow to work with ARM, with a foundry. So we got the world's leading foundry, we have the world's leading IP provider, and you have the market leading, world leading software provider all joined at the hip to make sure that the 20 nanometer high performance ARM A15 Cortex is running at the best performance, power, and area possible.